In 1988, the final problem of the International Mathematical Olympiad could be written in a single line. It looked like an ordinary divisibility question, but 189 of the 268 contestants scored 0. Let a and b be positive integers, and suppose that the quantity a squared plus b squared divided by a times b plus 1 is an integer. We have to prove that this integer is a perfect square. Before we try to factor anything, let us give that integer a name. Call it k. So the original condition simply says that the fraction is equal to k. Now clear the denominator. We obtain a squared plus b squared equals k times the quantity a times b plus 1. Expand the right-hand side, then move every term to the left. We get a squared minus kba plus b squared minus k equals 0. Now hold b and k fixed. Instead of thinking of a as a fixed number, replace it with a variable, x. The same relation becomes x squared minus kbx plus b squared minus k equals 0. This is a quadratic equation in x, and we already know one of its roots, x equals a. But every quadratic has another root. Could that second root also be an integer? Let us call the other root c. For the moment, c is only a name. Vietta's formulas tell us that the sum of the two roots is k times b. The two roots are a and c. So, a plus c equals kb. Therefore, c equals kb minus a. And this is already important. A, b, and k are integers, so c is an integer as well. Vietta's formulas also give us the product of the roots. So, a times c equals b squared minus k. Now, the original equation is symmetric in a and b. That means we may assume, without loss of generality, that a is at least b. Let us first examine the case where b squared is greater than k. Then, b squared minus k is positive. So, a times c is positive. And because a is positive, c must also be positive. Now use the product formula again. c equals b squared minus k divided by a. This is less than b squared divided by a. And because a is at least b, b squared divided by a is at most b. So we have 0 is less than c, and c is less than b. But remember, c is a root of the very same quadratic equation, so it satisfies c squared minus kbc plus b squared minus k equals 0. Rearranging this gives b squared plus c squared equals k times the quantity bc plus 1. This has exactly the same form as the original equation. So the new pair, b and c, gives the same value of k. But now, the second entry is smaller. We started with a and b, and we produced b and c, with 0 less than c and c less than b. That is the jump in Vietta jumping. Now repeat the same jump whenever the smaller number squared is greater than k. Each time, the smaller positive integer becomes strictly smaller. But positive integers cannot decrease forever, so eventually the process must stop. Let the final pair be a and b, with a at least b and b squared at most k. This final pair still satisfies the same equation. A squared plus b squared equals k times the quantity ab plus 1. Move the mixed term to the left and factor a. We obtain a times the quantity a minus kb equals k minus b squared. Because b squared is at most k, the right-hand side is non-negative. And because a is positive, a minus kb must also be non-negative. So a is at least kb. Now, suppose for a moment that k were strictly greater than b squared. Then k minus b squared would be positive. That means a minus kb would be a positive integer, so it would be at least 1. Therefore, k minus b squared equals a times the quantity a minus kb, which is at least a. And a is at least kb. Since b is a positive integer, kb is at least k. So we would have k minus b squared is at least k. But that is impossible. K minus b squared is strictly smaller than k. So k cannot be greater than b squared. But we already know that b squared is at most k. Therefore, k equals b squared. So k is a perfect square. And because k was the original quotient, the quantity a squared plus b squared divided by ab plus 1 must always be a perfect square. That is Vieta jumping. Use the second root to create a smaller solution. Then descend until only a square remains. There is one last surprise. The jump can also be run backward. For k equal to 4, the pairs 8 and 2, 30 and 8, and 112 and 30 all give the same quotient. So the proof is not only a proof. It is also a machine for generating infinitely many solutions. And that is the secret hidden inside this innocent-looking fraction.